First you have to understand stress is not defined like for a body. It's not like if you apply force and you ask what is stress, your answer is simple, force applied divided by area. That is not how it is defined. Stress, first of all, is always defined at a point. At a point. Let me give example. Suppose I give you a wire which is cylindrical in shape. Suppose I apply force like this here, F. It will stretch. Yes or no? It will stretch. Now, if I want stress, what is stress like this? That is a very weakly defined question. Weakly defined. You have to say stress at which point. So if you want stress here, let's say, at P, what you have to do? Draw this line, calculate tension force here. Now tension is either here or here depending on the system. So let us choose this as system. This part as system. Tell me the forces. Here left side applied force, right side tension, because this part is pulling this part. So at this point tension is T. Now the whole system is not accelerating because net force is 0. Right? Half of this part will go here, half of that part will go here. Center of mass will remain at rest because net force is 0. But once they stretch, equilibrium will reach CC. When I pull this, after some time equilibrium will reach, where my applied force will equal tension force. Then the system will come to equilibrium. So this is when we have reached equilibrium. That time acceleration should be what? 0. So now tell me who will balance this T? F. So what is T equals to? F. At which point? This point. So what is stress at that point? Actually T by A. So it is the internal restoring force per unit area. But in this example, it is also applied force by area. In this example. Suppose I choose another point. Same answer will come or different answer? If I choose another point, same answer will come or different answer? How different will come? If you choose this point, you will remove this part and you will take this as system. Again you will draw free body diagram. Here F, here T. Again all the parts are in equilibrium. Again T will be what? F. So in this particular example, tension everywhere in the wire is same. Therefore, you can say stress in the wire is this much. Because it is everywhere same. But that is only a particular case. There are many cases where tension may vary from point to point. So this example is what? Stress is everywhere same. Everywhere same. So if stress is everywhere same, then you can define stress as applied force per unit area. Since this force is perpendicular to the surface, people also call this normal stress. Perpendicular to the surface, right? Then here, this is stress, symbol we write sigma. Sigma. Strain is defined in this example as change in length by original length. So this original length when no forces were applied was L. After you apply forces and equilibrium has reached, the length is L plus delta L. So this is your strain. Now there is a law called Hooke's law. Hooke's law says within elastic limit, matlab within the point where the body will go back, the stress is directly proportional to the strain. So ratio will be what? Constant. That constant is called modulus of elasticity. In the case of this rod, it is called Young's modulus. Stress by strain. In this particular example where stress is everywhere same, what is the stress? F by A. What is the strain? Delta L by L. So if somebody will ask what is change in length, what will you say? Cross multiply FL by YA. Yes or no? Now tell me something. Suppose I double the length. What will be Young's modulus of the wire if I double the length? Okay, different question. In a resistor, we know V is proportional to I. Suppose I double the current. What will be change in resist? What will be resistance? So, about current is doubled. What will be change in resistance for this resistor? It doesn't change because it came as a constant of proportionality. So, when you change the current, what will change? Voltage will change. Or if you change the voltage, current will change. Resistance ratio should remain constant. So, this Young's modulus came as a what? Constant of proportionality, guys. Therefore, Y will remain same. This is material dependent, guys. Material dependent. Of course, if you change the wire, then Young's modulus will change. Like if you change the bulb, resistance will change. Now students, again, this is only in which case? When stress everywhere is same. Then only you can calculate change in length this way. Sometimes they will ask energy stored. To find energy stored, in this particular example again, when stress is everywhere same, look at that formula for delta L. Can I write F, this formula, or this formula? Can I write like this? Ya by L into delta L. Now compare this with spring force. You pull here with F, your friend will pull here with F. Spring will stretch. In equilibrium, this F will be balanced by spring force. So what will be F that time? K into X. X matlab what here? Change in length. That means K will play the role of what here? Ya by L. So a solid wire with Young's modulus is like a spring with spring constant how much? Ya by L. That's why in physics we say spring constant is inversely proportional to length of the spring. So if you have a spring of length L, you cut into two parts. Spring constant will become double because length has become half, K will become double. So you can consider a rod, but it has to be elastic. It should have Young's modulus. Inextensible wires means what will be delta X or delta L? 0. Even if tension is there, delta L is 0. When is that possible? If delta L is 0, even when there is force, length and area will always be there, brother. So even when force is there in the wire, delta L is 0. That is only possible when Young's modulus is infinity. So the wires that we studied in Newton's law chapter were ideal wires. They don't exist, such wires, where even if you apply force, it's not changing in length. Because their Young's modulus is how much? Infinite. In other words, spring constant is infinite. What is the advantage of this, knowing this? Because now energy stored, how can you write? Energy stored, how you can write? Half K X square. So this is the formula for energy stored in a what wire? Stretched wire. Again and again I am telling, all this is under the assumption that at every point stress is same. Now one very important term is there, energy stored per unit volume. Like we did in capacitor, inductor, it is called energy density. So how to write energy density now? Small u. Energy stored divided by volume. What is energy stored? Half Ya by L delta L square. What is volume of a cylindrical wire? Area into length. Area cancel. So what is energy stored? Half Y delta L by L is strain. So I can write strain square. Strain is what? Delta L by L. Some people also remember this by writing Young's modulus is what? Stress by strain. One strain cancels. So everybody remembers this popular formula. Energy density in stretched wire. Half into stress into strain. So one example where stress everywhere is same is what? Take a rod, apply same force F in opposite direction. Same magnitude. That will make sure tension everywhere is same. Another example where tension everywhere will be same and you can use all these formulas is this wire. You have a light wire but it has Young's modulus area length. Just like springs comes with spring constant, elastic wires comes with YAL. Now here you have kept a heavy block. This wire's mass is negligible. So you can neglect compared to this block's mass. Now let me ask, what is tension here if I ask? How much will you tell here? Mg, because you will draw free body diagram of this block. T up, Mg down. Here if I ask, you will draw free body diagram of this part. Tension you will show up T. Mg what will you show? M and this Mg, but I told this M is negligible. Then what it will be? Mg. Matlab tension here is how much? Mg. Matlab tension here was how much? So everywhere what it will be? Mg. Then we can use our standard formula. So if somebody will ask what is stress, you don't have to mention at which point. Directly you can say stress is T by A. This time what is T? Mg by A. Mg matlab weight of this block. Before it was F, remember. By the way, that F that you applied, you can do the same thing for this also. This also. You may think, sir, where is the other person pulling this side? Why you need other person? Wall will pull this side. Because when you pull the rod will pull the wall this way. So wall will react and pull the rod this way. So this also will work. Whatever I did for previous case, same you can work for this case. Okay, stress I found. What will be? Because stress is everywhere same, I can use directly formula for change in length. What is the formula for change in length? I told FL by YA. What is F in this example? Mg. I hope I am right. Young's modulus is stress by strain. F by A delta L by L cross multiply delta L here, Y here. Correct only. So Mg L by Ya. Sometimes they will give you radius of this cross section. That time A will be what? Pi r square. Okay guys. Now life is not always jingalala. Okay na. Sometimes it will be more challenging. So let us now discuss what will happen if tension changes from point to point. So here is a cylindrical rod. Young's modulus Y, original length L, area of cross section A. Here I apply force F, here I apply force 3F. First you have to find tension or stress, but this time you have to mention at which point, because now tension from point to point will change. You will see. So stress at P, find. Now you will ask, where is P, sir? P is here at a distance L by, let's say at a distance X. X can be any fraction of this L. L by 2, L by 3, any distance. Then you have to find delta L of the rod. Then you have to find energy stored in the rod. So these three things we are going to calculate. None of the previous formula will work. Why? Look here. For this system, tell me acceleration of the system right side. 3F minus F divided by mass of the wire. So 2F by M. Everybody clear with this? Newton's second law for whom? Whole wire. So first I have chosen whole wire as system. When you connect blocks with another block with string and you pull one block, we do the same thing. If people ask tension on this block, first we find A of the whole system. Then we apply Newton's law for one block and find T. Same story. First find A of the whole system. Total external force 3F minus F. Sometimes they will apply F here only. Then what will you write? 3F plus F. Now tell me, if I take this much as system, here T will act because this is not here. Here force is 3F, not here. No, here though this part will be pulled by this part this side. So here tension T, here F. By the way, don't be surprised if T comes minus, because this is rod. In rod, tension force can be pushing also, because it is rod. String and all, what happens when you push? It becomes loose. Rod can sustain tensile stress also, compressive stress also. So don't be surprised if T comes negative. So F here, T here. Correct, students, still here? Okay, now apply Newton's law to this. T minus F equals to mass of this part, you tell. Total mass by total length into length of that part. How will you find mass of this part of the wire? Total mass by total length into length of this part into A. What is A of the system? 2F by M. Everybody clear how I use Newton's law? Total force equals to mass of the system into A. A is common for everybody. Mass of this part, how did I find? From unitary method. So M will cancel, what will be tension? F will go this side, F bracket 1 plus 2x by L. Everybody clear? Yes or no? Once you know tension, what will be stress at that point? Tension by area of cross section. So what will be stress? F by A bracket 1 plus 2x by L. Did you now understand why stress changes from point to point? Because it has x. Can you plot a graph between stress and distance if they ask? Distance from the left end. Quickly tell me, when x is 0, what is stress? F by A. And when x increases, linear stress will increase linearly with slope how much? 2F by AL. So graph will be like this. Okay. First question done. Second question is what? Delta L. Now students, because stress changes from point to point, strain also will change from point to point, because stress and strain are directly proportional. Now you will say, but strain is delta L by L. How do you know? What do you mean by strain at a point? Look here. So the actual definition of strain at a point, how to define? Well, very simple. At that point, let's say you consider a small piece of this rod, length dx. When no forces were applied, the length of this small piece was dx. When forces will be applied, here tension will act. Because of the tension forces, this piece will slightly increase in length. What will be that? What will be the change in that length of this small piece? Let us write is delta dx, because I don't have any other good symbols. So delta dx represents what? Change in the length of this dx at this point. Remember, you can take as thin as possible, no, close to that point. Divided by what? Strain. Change in length by, what is the definition of strain? Change in length by original length. So what is, I have chosen this part as the length. So what I should divide by? So how will you calculate change in length of this small piece? Strain into dx. And if you want to know total change in length, what will you do? Total change in length, what will you do, guys? You will keep adding the changes in the length of all these pieces. Directly we cannot find change in length now because stress at different points are different. So strain will be also different. Strain different matlab what? At different point, same dx will expand by different amount, will stretch by different amount. It's like saying as you move from this point to this point, force changes. Then directly we can't write force into displacement to find work done. First we should find small work done for small displacement. Then we have to integrate. So first we have to find change in length for a small piece at a given point. Then to find total change in length, what will you do? Integrate the changes in dx from 0 to L. That means we have to write what? What is change in dx? Strain into dx. By the way, students, something interesting did you notice? If strain was constant everywhere, which will happen if stress was constant everywhere, like previous questions, then strain will come out. What will you get? L. Then what will be strain? Delta L by L. But that is not always true. Understood? Now, strain how to write? Well, stress I know anyways. At this point I know stress. At distance x, no. I know stress already. So strain how can I write? Young's modulus is what? Stress by strain. So what will be strain? Cross multiply. Stress by Young's modulus. Constants you take outside 1 by y. Integrate stress with dx. And what is stress? Tell me directly. F by a I can take outside. Integral 1 plus 2x by L. Yes or no, students? This integration is not big deal for you people, isn't it? So make sure to write strain in terms of stress. Why, sir? Because we know the formula for stress. Now anyone can do this. Tell me, let us try to do this directly, students. Integral of 1 dx from 0 to L will be L plus 2 by L will come outside. Integral of x from 0 to L will be what? X square by 2, L square by 2, correct? 2 cancel, 1 L cancel, L plus L, 2L. What is change in length? 2 FL by YA. Now one shortcut you say to find delta L. But this shortcut will only work if your stress varies linearly. X has power 1, so it will work in this case. How to remember the shortcut? Well, if stress was everywhere same, what was delta L I told? FL by YA. If stress changes from point to point, like in this example, what you do? F average you write. You will get same answer. Like in this problem, what was F average? What was the forces at the two ends? F and 3F. Both were tensile force, so you have to add. You will say, sir, but they are opposite in direction. That is when you apply in Newton's law. Here, both are going to stretch the wire, and we are calculating change in length. So if both are tensile force, you have to add, remember, otherwise gone case. So shortcut for calculating average force, which increases the length of the wire, is F plus 3F divided by 2, how much? 2F. Same answer. So you can skip so much of integration. Yes or no? Energy stored, I will just write the formula, you guys do the integration. Okay, because anyways it will be practice for you for integration also. So energy stored. Directly we cannot calculate energy stored now because stress changes from point to point, strain changes from point to point. So first we have to calculate energy density. Energy density, what is the formula you guys told? Half stress into strain. Energy density means what? Energy per unit volume. So now tell me, in this rod, what is the energy stored in this small volume dx, whose area is A, that side. Back side area is A, no, this side. So what is energy stored in this volume? du. Energy stored per volume into dV. So now total energy stored, how will you find? Integrate this. Finished. Half will come outside. Sigma, what is strain? Stress by Young's modulus. And dV of this small section, how will you write? A into dx. Constants you take outside. Half A y integral sigma square dx from 0 to L. Sigma we already found. Substitute, integrate. That you can practice. You will get 3 terms because it's whole square, na? So a square plus b square plus 2ab formula. But still, easy integration you will get. Practice once. Okay. If a wire of mass m is held vertically like this, directly. First of all, can we use our normal formula of F L by YA? No, because now tension will change from point to point. Previously I gave you light wire with a heavy block. Now it is just a wire. Original length is L, let's say, when it was horizontally. Vertically, the moment I keep, what will happen? Gravity will pull it. So tension will be developed everywhere. But tension here will be what? There is nothing here which is pulling it down. That day also I think I told you, suppose she is hanging from that, what is that called? Plank, like this. Below that she is holding her leg. Below the Dania is holding her leg. Her, who will be under maximum tension? Hands. Her, next yours, then next your hand. Your feet will be aram, relaxed. That will be the most stress-free point. So here tension is what? 0. Here tension is what? mg. So if somebody will ask you find change in length, what will you do? First, at some distance x, find tension here. What will be tension there? Take this much part as system. Tension here will balance weight of this. What is weight of this? Total mass by total length into length of this small part into g. That is tension. So what will be stress? Tension by area. So that will be stress at this point, which changes with x. Then what will you do? Take small dx here. Find change in length of dx. Then integrate that from here to here. Unnecessary. We have our shortcut. So what was the shortcut formula for delta L? Average force L by YA. What is average force? Here tension 0, here tension mg. So what is average force? mg by 2 L by YA. Understood everyone? But please try to do integration and check. You will get same answer. Which integration, sir? Arre, delta L was what I told. Integral of change in dx. Change in dx was strain into dx. Strain is stress divided by Young's modulus. Put this stress here and then do integration. You will get this answer. But shortcut is better or not?